Hi everybody, Mr. Gerhard here, and we're going to talk a little bit about logarithms, which is section 7.4 in our book. Logarithms were invented to help us solve exponential equations. And so when I look at some easy exponential equations, I can get something that looks like this: 2 to the 4th equals x, and we all know that 2 to the 4th is equal to x, so that's good. Or 2 to the 2nd is equal to 4, I'm sorry. We also know that 2 to the 3rd is equal to 8. And those are easy numbers. The problem comes in when we have something like this, where it says 2 to the x equals 6. Because we know that if x were equal to 2, then we'd have 4. And we know that if x were equal to 3, we would have 8. So it's got to be somewhere between 2 and 3, but where? We don't know. And so that's where logarithms come in. And so logarithms were invented to help us solve equations like this. So the definition of a logarithm is if we let b and y be positive numbers with b not equal to 1, the logarithm of y with base b is denoted by log base b of y and is defined as follows. Log base b of y equals x if and only if b to the x equals y. And so here's our base of our exponent. There's our exponent, and that's what it's equal to. And so what we're going to do first is we're just going to practice going from logarithmic form to exponential form and back to logarithmic form, okay? Knowing that log base b of y equals x is equal to b to the x equals y is very, very important, and we're going to see that on the next page. Up here you can see our statement or definition of a logarithm. Log base b of x equals y if and only if b to the y equals x. So here's our base, here's our exponent, and that's what it's equal to. And so that's what we're going to do to begin. If this is in logarithmic form, log base 2 of 8 equals 3, we need to put it in exponential form. So we start with the base of the logarithm, 2, raise it to the 3rd power, say that's equal to 8. And we know from our work with exponential functions that 2 to the 3rd is equal to 8. And so there's our equation. And this is in logarithmic form, this is in exponential. Here's another one. 12 to the 1st power equals 12. So in logarithmic form, we say log base 12 of 12 equals 1. In exponential form, we would say 12 to the 1 equals 12. Now these get a little bit trickier because now we're looking at b to the y equals x. We have to put it in this form. So what I do is I identify the b first. So let me just change colors here. I'll go to blue. All right. The base is 4, so I know that's going to be my b. And then we go across the equal sign and then back to what the exponent is. So we're going to write this out as log base 4, we subscript that a little bit, of 1 equals 0. And if I wanted to, I could check by saying 4 to the 0 equals 1, and that's what I have over here. Same thing over here. 1/4 to the negative 1 equals 4. 1/4 is my base, so I'm going to say log base 1/4 of 4 equals negative 1. And if I check, a 1/4 to the negative 1 is equal to 4. And so this is in logarithmic form, this is in exponential form. We can go back and forth, and that's going to be kind of key when we start solving logarithmic equations. Now, how do we evaluate logarithms? Well, we have to think again in terms of what a logarithm truly means. So let me copy and paste this over here. Copy. Go to the next page and paste, because we always want to have that there. Let's paste it, throw it right here. Always good to kind of have that at the top. So now we know that log base 2 of 32, we don't know what that is. But what I can do is I can think 2 to what power is 32. That's what I'm thinking. So think, should put a little thought bubble up there, but think 2 to what power is 32. And if you know your powers of 2, you know 2 to the 5th power is 32. And so then what I'm going to do is I'm going to say 2 to the 5th power is 32. So the log base 2 of 32 is equal to 5. And I've just evaluated that. Same thing here, 27 to what power, we don't know, is equal to 3. Well, 27, question mark, equals 3. Now, 27 divided by 9 is 3, but we don't know that as an exponent. We do know 27 to the 1/3 because that would be the cube root. The cube root of 27 is equal to 3. And so our answer here is 1/3. Now, the other part that we have an issue with is this part right here. Common logarithms and natural logarithms. We use base 10 a lot, and we also use base E a lot. And so mathematicians got to the point where they're like, I don't want to keep writing base 10. I don't want to keep writing base E. They kind of whine like, some sophomores I know. So anyways, what they do is they said, we're just going to not write the 10 anymore. They rebelled and they said log of x is equal to log base 10 of x. So we're just going to call it log of x. And log base E of x is going to be the natural log of x, and we're going to call it ln of x. And so those are two logarithms where we don't see the base. We don't see the base. We just know that it is log base 10 or log base E. We don't ever really write it this way anymore. Okay? And so now when I see this log base 10 of x, or the common log of 12, I'm going to go ahead and say 10 to what power is equal to 12? And that doesn't go in evenly. 12 is not a nice number. And so what I have to do is I have to use my calculator to do that. And I'm going to click over here and show you what that looks like. You can't do that. So I'm going to switch over to my calculator, and I'm going to go over here. And if you notice on the Inspire, it says log in blue letters and ln above in blue letters here. And so to get to the log button, I'm going to just do Control 10 to the x, and you notice on the Inspire it gives us a log and then a base and then something here. We don't actually have to put a base in there because automatically if I type in 12, it automatically puts in the log base 10. Now if you have it in 84, there's a log button, so you just press log of 12, and you can see it's some crazy decimal. It's an irrational number. And we're going to round it to 3 decimal places, and we're going to call it 1.079. So let me flip back here, and we're going to say this right here is approximately, we'll use squiggly equal signs, 1.079. And that's our approximate answer. Same thing here, natural log of 0.75. If I flip over to the calculator, we can say Control natural log of 0.75. Click enter, and you get negative 0.288 if I round to 3 decimal places. So I'm going to go back over here and I'm going to say approximately equal to negative 0.288. Okay, and so that's how we use our calculator to approximate the logarithms. And then the last thing that we're going to do is we're going to find inverses. To find inverses, we still switch x and y. That was always our first step before. But then we're going to put it in exponential form and then solve for y. And putting it in exponential form is going to help us solve for y. So again, we have our definition of a logarithm, log base b of x equals y. If and only if b of the y equals x, you should be saying that in your sleep. First step, switch x and y. So x equals 4 to the y. Then we're going to put it in exponential form, or logarithmic form in this case. So we're going to say the log base 4 of x equals y, because 4 was our base. And then we go across and we can check by saying 4 to the y equals x, doing our little circle thing here. And that's our inverse function. Log base 4 of x equals y, and y equals 4 to the x. Here, if I switch x and y, I get x equals natural log of y minus 5, put in exponential form. Now remember, our base is e here. We don't write it, but e to the x equals y minus 5. And then we got to add 5 to both sides. E to the x plus 5 equals y. And that's our inverse function. So that's a little bit about logarithms. I hope it helped, and we'll see you soon.